Good evening, one and all. Today is 12th June 2023. We are going to see lecture number 30 today. We are in the fifth module of electric and hybrid vehicle for professional elective 3. In that, we are in the fifth module, which is called as hybrid drivetrain designs. In hybrid drivetrain designs, we know there are two topics mainly. One is series hybrid electric drivetrain design, another is parallel hybrid electric drivetrain design. We are in the series hybrid electric drivetrain design, which is the first part of module 5. Already we have covered 2 lectures under this series hybrid electric drivetrain. We have completed operation patterns, control strategies. There are 2 control strategies, PPS control and thermostat control. Today we are going to see the last topic in series hybrid electric drivetrain, which is called as sizing of the major components of this series hybrid electric drivetrain. There are mainly 3 things that are actually deciding the performance of series hybrid electric drivetrain. Number 1 is power rating design of traction motor, number 2 is power rating design of engine or generator, and third one is design of peaking power source or PPS. We have already seen under control strategies that PPS means the secondary source, which is generally battery, which is called as a peaking power source, because whenever peak demand of power is there, at that time only this source comes into action. Otherwise, most of the time the primary power source, which is engine generator or engine, this only gives the power supply to the final drive element. So today we are going to see the design considerations of power rating design of traction motor, engine generator and peaking power source. So you might find the lecture a little difficult because there are a lot of equations, there are a lot of considerations, but one thing I'd like to tell you, all the fundamentals that we are going to see in this lecture, you have already studied all these fundamentals in the previous lecture, starting from module 1 to module 4. Only thing is, for series hybrid electric drivetrain, how the parameters are going to get modified little bit, that we are going to see in this lecture. So power rating design of traction motor. The power rating of the electric motor drive in series hybrid electric vehicle is determined by mainly 3 parameters. Number 1 is the vehicle acceleration performance, traction motor characteristic and transmission characteristics. At the beginning of the design, the power rating of the motor drive PT has to be decided, that how much power actually or average power we want from the vehicle. So this is a very important formula we have already seen. For IC engine based vehicle, we know it is PT is equal to delta M by 2 TA. TA is the acceleration time, M is the mass of the vehicle, delta is a proportional constant for rotational to linear vehicular speed conversion. VF is velocity, VB is also the base speed. VF is actually the mainly the velocity which takes the vehicle forward. So this is VF square plus VB square plus in case of IC engine based vehicle, this 2 by 3 is not there, it is mgfr VF. That means the forward velocity, rolling resistance, mass and acceleration constant. So this 2 by 3 comes only in case of electric vehicle. Similarly, in case of IC engine based vehicle, this 1 by 5 is not there, it is 1 in case of IC engine based vehicle. In case of electric vehicle, it is 1 by 5. Then rho A, CD, A, V, F, cube, all those things are as it is, as we have found in case of IC engine based vehicle. So this PT formula is max actually what we find in case of electric vehicle. In module 4 first part, we have seen this equation. So according to the acceleration performance, that means how fast you want the acceleration to happen. Faster the acceleration, TA value will be lesser. Definition of TA, acceleration time, that is, it is the time taken by the vehicle to go from 0 to 100 km per hour speed. So lesser is the acceleration time, better is the acceleration characteristic of the vehicle. So according to this acceleration performance or smaller acceleration time, the vehicle from 0 speed to a given speed, this PT is decided. So deciding factor for PT is actually the acceleration time. Here M is the total mass of the vehicle in kilograms. It includes the load, the passengers, the vehicle chassis and all the weights of the vehicle. T is the acceleration time in seconds, VB is the vehicle base speed. Base speed is the highest speed under any gear. So for lower gear we find base speed is smaller, for higher gear base speed is higher. VF is the final speed of the vehicle during acceleration in meter per second. So VF is actually the maximum speed and VB is the maximum speed under a gear. So VB is generally less, VF is generally very high. VB can be 30 km per hour, 40-50 km per hour, and VF can be 200 km per hour, like that. G is the gravitational constant, 9.80 meter per second square. FR is the tire rolling resistance. Rho A is air density, 1.202 kg per meter cube. AF is the front area of the vehicle in meter square. CD is the aerodynamic drag coefficients. The first term in the above equation, PT, represents the power used to accelerate the vehicle mass under a certain time. The second terms represent the average power for overcoming the tire rolling resistance, and the third term represents the aerodynamic drag. So PT is actually comprising three terms. First term is the acceleration mass power, second term is the rolling resistance power, so and third term is the aerodynamic drag. So second and third term is actually going in the negative direction. They are actually the power loss, and first term is actually the power which is used for tractive or traction of the vehicle. We have seen this graph. In this graph you are finding that the tractive effort versus or tractive power versus two gear transmission system. So you are finding here one graph is A, B, D, E, F as shown here. This is one characteristic, that is the characteristic for the first gear. This is another characteristic for the second gear, which is C, D, E, F, G. So here you are finding it's a two gear transmission system. So first gear, that is AB, DFG cycle, is having base speed of around 30 VB1. The CD, EFG is having base speed around 45 km per hour. Maximum speed is around 180 to 200 km per hour. And you are finding this is the AB region is the constant torque region for VB1, that is the base speed 1, and CD is the constant torque region for base speed 2. In case of the first gear, which is AB, DEF characteristic, you are finding that maximum tractive effort at the starting is 8 kilonewton, and the same thing for the second gear is 5.3 kilonewton. So increase in the base speed actually will reduce the initial tractive effort or kilonewton. So AB or CD region is called as a constant torque region. Then BDEF or DEFG region is called as a constant power region, or which is also called as increasing speed region. In this case we are finding the motor speed ratio is x is equal to 4. How is it found out? So we are finding that this is a two gear system and highest gear is second gear, and this is having base speed around 45 to 50. So highest gear base speed, that is VB2, is the highest gear base speed around 50 or 45 km per hour, and here maximum speed is around 180 to 200. So 180 to 200 divided by this 45-50, if you do, it will come around 4 as an integer factor. So that is actually called as a motor speed ratio, which is x is equal to 4. Had it been a single gear system, that means only VB1, which is 30, the motor speed ratio would have been around 180 or 200 divided by 30. So it would have been around 6. So higher is the speed ratio, means it's a single gear transmission system. Lower is the speed ratio, means it is more number of gears are there, or it's a multi-gear transmission system. We know that a lower gear actually can ride for higher climb, or it can take on higher gradient. That means more is the slope, bigger is the slope, we have to keep the gear in a lower side. It is because you can see here the first gear is producing tractive effort of 8 kilonewton, second gear is having tractive effort, highest tractive effort as 5.3 kilonewton. That means if there is very high steep, then we have to keep the vehicle in the first gear, then it will be having a better riding characteristic. So here we find during the acceleration, starting from a low gear, that is the first gear, tractive effort follows the sequence A, B, D, E, F. At point B, so you are finding at point B the motor reached maximum speed at low gear, which is called as VB1, and then transmission is shifted from constant torque to increase in speed, or constant torque to constant power region. Here the base speed is VB is equal to VB1. When the next higher gear, that is the second gear transmission is used, the tractive effort follows the curve C, D, E, F, G. In that case, base speed Vb is equal to Vb2. A very important note is given, that is for a given final speed during acceleration of 100 km per hour at point E. So this is a calibration kind of speed, 100 km per hour. Some very special or specific thing is happening that you have to understand. For a given final speed or for a given speed, that is kind of, you can say not final speed but intermediate speed, the vehicle with two gear transmission will have a short acceleration time. So if you find it's a two gear system, it will be accelerating faster. So the vehicle with a two gear transmission will have a shorter acceleration time. Shorter acceleration time means vehicle will be able to accelerate faster. The produced tractive effort at low speed at low gear ABD is larger, that is 8 kilonewton, than two gear system CDE, where the value is 5.3 kilonewton. So there are two conclusions, that is two gear transmission system will have a shorter acceleration time, that means it will reach 0 to 100 km per hour faster compared to first or single gear system, which will reach 0 to 100 km per hour speed in a slower fashion. That means higher the gear, reaching the higher speed will be in a faster rate, or TA will be smaller. This is one conclusion. Second conclusion is the tractive effort at low speed, that means first gear is higher than the tractive effort at second gear, which is 5.3 kilonewton. So all this actually we know, but under series hybrid electric drivetrain, if we are checking the engine characteristics, all these things we have to discuss. So here you are finding two graphs. You are finding left side is both are actually left side is two gear system. The same graph we have seen in the previous slide also. X is equal to 4, the same graph actually shown here. So only one addition I will speak here is left side vertical axis is tractive effort in kilonewton, and right side of the vertical axis of the left graph is actually giving you tractive power in kilowatt. So left side of the left graph it is kilonewton, and right side of the left graph y axis it is tractive power in kilowatt. So you are finding here initial first gear kilowatt is around, you can say 20, 40, 60, 80, 100, it is around 160 kilowatt. Okay, and you are finding for the second gear it is around 110 kilowatt. So this is the difference between first gear and second gear for speed, torque, power characteristic of an electric motor. So this can be asked in the exam, that is speed, torque and power characteristic. So there should be two y axis, one is tractive effort, that is how much is the output power generated, tractive power you can say kW. Okay, so this is kilonewton, newton means force, so force, power and vehicle speed, all these three characteristics are shown together. So this graph was explained very elaborately in the previous slide. So power turn of traction motor versus speed ratio of a drivetrain. So what is this right side graph? This is showing 2, 3, 4, 5, 6. This is nothing but speed ratio. So here you are finding x. So x axis is nothing but x, which is nothing but speed ratio. So speed ratio 2 means it's higher gear. That means here if you consider that maximum speed is around 200, so 200 by 100 is equal to 2. That means here the base speed is 100 km per hour. That's why speed ratio is 2. Here the base speed is 20 km per hour. So 200 by 20 is equal to 10. So this is lower gear and this is higher gear. And you are finding whenever the higher gear is there, in that case to generate some kind of vehicular power, we have to use more effort, we have to give more effort. That means to create some acceleration when the vehicle is in higher gear, okay, the more amount of energy has to be given, because you are finding here the slope of the graph is very high, whereas whenever you are in the lower gear, at that time to create high acceleration, the change in energy is very less. That means whenever you are in lower gear, very effortlessly you can accelerate the car. Effortlessly means it will not create pressure on the vehicle, because in this case actually torque is already very high. That's why whenever we want to climb a hill, at that time we have to keep the vehicle in lower gear, because acceleration in that case is easier. Whereas whenever you are in the higher gear, at that time to create the same amount of acceleration, you have to waste or you have to utilize more amount of fuel from the engine or for the engine. So this is what is this graph all about. That is for higher gear or lower value of x, we have to waste or we have to give more amount of energy to cause an acceleration, whereas whenever we are in the lower gear, to cause very big acceleration we have to use very small amount of energy, because vehicle is already in a high torque mode. High torque mode, acceleration is easy. So t is equal to 10 seconds, that is the acceleration time. M is equal to 1500 kg. This includes driver, passenger, vehicle, load, everything. Rolling resistance 0.001, so very conducive kind of rolling resistance. The road is very smooth kind of thing, very good for driving. CD and AF, they are aerodynamic factors, they are 0.3 and 2 meter per square. Figure B, that is the right side, which is actually comparing the higher gear with the lower gear operation of power generation in the vehicle. So figure B shows an example of the power rating of the motor versus speed ratio. Speed ratio is defined as the ratio of maximum speed to the base speed as shown in figure A. So from the right side, what you have to say is, for higher gear to generate the acceleration, it takes more power from the vehicle. That means efficiency becomes less compared to the lower gear. That means if you want to really accelerate the vehicle, if you are in the lower gear, it will eat up less amount of fuel. This is what is the conclusion from this right side of the figure. Now, power rating design of the traction motor, already you know what is the grade power. So grade power is mgfr cos alpha. This is nothing but the rolling resistance when the vehicle is at inclination. So the rated power determined by PT equation is only to estimate for meeting the acceleration performance. In special acceleration such as off-road, military vehicle, cross-country operation may be the primary concern. So in this case, the traction motor must be powerful enough to overcome the required maximum grade of an off-road trail. That means in this case, the alpha thing will come into picture. So what is the alpha? Alpha is nothing but the banking, or alpha is nothing but the gradient of the road. So in that case, how much will be the traction power? So previously we did not consider the alpha value. In this case we are considering what is the grade power. That means whenever the vehicle is on hill, that means it is going to cross some hill, or it is inclined going up. In that case, how much will be the power required by the vehicle? So it is mgfr cos alpha. This is called as a rolling resistance component. So cos alpha is nothing but the cos of the angle of the road, that is gradient. Aerodynamic resistance is not dependent on alpha directly, but this half factor is coming. So half rho a CD AF V square, and this mg sin alpha is the weight component of the vehicle. Mg sin alpha, m is the mass, multiplied by v. V is nothing but the forward velocity of the vehicle. This is in watts. So this is the grade power. Here alpha is the ground slope angle, v is the vehicle speed in meter per second specified by the gradability requirement. Assume a vehicle is climbing its required maximum slope of 60% or 31 degree. So this is one thing you have to understand, how this 31% is called as 31 degree is called as a 60%. So tan of 31 is equal to 0.6. So whenever it is said that the vehicle is on 60% slope, that means you have to take the tan inverse of this, and the unit will be in degree. So tan inverse of 0.6 will be 31 degree. So in that case you have to say that whenever I am saying 60% means first you have to divide the percent by 100. So 60 divided by 100 is 0.6. Then you have to take the tan inverse of that. Whatever angle you get, that is actually the value of alpha. So if I say 70%, whenever I am saying 70% at that time, first you have to get 70 divided by 100, that means it is 0.7. And then you have to take tan inverse of 0.7. Whatever degree you find, maybe around 39, 40 or whatever, that will be the angle of the road. So this is a new thing you have learned. So in real life operation, what we are actually studying is the power rating design of traction motor. In real life operation for off-road driving. Off-road driving means we are not on road, we are in a challenging terrain. That means it can be high steep, it can be jungle, it can be desert, or it can be clay, mud and all those kind of things, where actually the secondary source comes handy. So whenever the vehicle is on highway, flat road, at that time only the primary source is enough. Whenever it is on the challenging road, that is off-road driving, hill, jungle or desert, sand, clay, that time actually rolling resistance also becomes quite high, unpaved road, okay, a lot of adversities actually come into picture. In this case we actually get to know the real power of the vehicle. So the traction motor should be designed in such a way that it should be able to fetch best possible power from the vehicle source, and should be able to take the vehicle forward through the hill or through the climb, etc. So in real life operation, for off-road driving or usually unpaved road, rolling resistance is much larger than those of the paved road. Obviously paved road means rolling resistance is very small, it is the cement road and all. Whenever it is going off-road, at that time rolling resistance is becoming high. It is because of the off-road surface deformation. Surface deformation obviously will increase the value of Fr. Therefore, in the calculation of motor power required for gradability, additional resistance power should be added to reflect this situation. For 60% gradability at 10 km per hour, tractive efforts versus vehicle speed of a 10-ton military vehicle with different extended speed ratios and motor power rating is found by the equation shown in left. Larger extended speed ratios effectively reduce the power rating requirement of traction motor to meet the gradability requirement, which means that as speed on the max slope is smaller, the large extended speed ratio can be implemented either by the motor itself or multi-gear transmission. That means whenever you are finding that vehicle is going to travel through a difficult terrain means like a hill or a desert or clay or mud or that kind of thing. In that case, large extended speed ratios, that means you can say X value very high, that can be implemented either by the motor itself or by a multi-gear transmission. So in that case, actually there will be the real test of the traction motor and the power supply system. This characteristic also we have seen in case of chapter number 4, that you are having two graphs. The bottom graph is required by acceleration, top one is required by gradability. Here also we are finding the same thing, that is left side is the higher gear, that means this is having lower value of X, lower speed ratio, and right side is lower gear or higher speed ratio. In this case you are finding that for creating more delta Y, that means for creating more change in the speed or power, okay, there will be more change in the X. That means what you are finding is to create higher acceleration or to attain higher gradability, we have to use more power, we have to take more power from the source in the higher gear side. For the lower gear side, you will be finding that to create acceleration or to create higher gradability, we don't have to waste much power or we don't have to use much power from the source. That means lower gear is mainly for fast acceleration. Actually acceleration becomes easy at lower gear, but for higher gear the acceleration becomes difficult. That means efficiency actually is getting hurt whenever you are trying to accelerate in higher gear. That is what is the meaning. That means you have to remember this, efficiency of the vehicle or fuel efficiency of the vehicle is getting hurt if you are in higher gear and trying to accelerate the car in a very great extent. At lower gear, if you are trying to accelerate, you are not going to waste much of the energy, stored energy. But in higher gear, whenever you are trying to accelerate, you will be wasting much more energy, you will be reducing the efficiency. This is what is this graph about. So to ensure that the vehicle meets an acceleration requirement, for example 8 seconds, that means vehicle speed has to be increased from 0 to 48 km per hour in 8 seconds. So in this case TA time is defined differently, acceleration time. Instead of 0 to 100 km per hour, in this case it is 0 to 48 km per hour, so it is 8 seconds. Motor power rating requirement with different extended speed ratios on the paved road is also calculated using PT equation shown in the previous slide. It is obvious that the motor power rating is determined by gradability performance. That means how good the vehicle is depends on how good the motor is performing. This means that the power rating designed to meet the gradability will naturally meet the acceleration requirement. So we need acceleration more when the vehicle is actually riding on a hill. At that time, if you are able to accelerate easily whenever you are on hill, that time we can say that vehicle is a good vehicle or it's a high powerful vehicle. A fat man can run on plain road maybe easily. Okay, generally if it's a very big car, if it's very weighty, in that case for it to run with a very high speed on flat surface is easy. But the same car, very weighty car, if you are trying to put on a hill, That time if it can run very easily, accelerate very easily, then only we can say that this very heavy car is having good performance on flat road as well as on hill. That time we can say the vehicle is really powerful. Otherwise, if it runs very fast, if it runs with proper acceleration on the smooth road, but as soon as you put it on the hill, it cannot accelerate. This case we will say that vehicle or motor design or powertrain or drivetrain design is not proper. So it is obvious that the motor power rating is determined by gradability performance. That means how well we can accelerate on the hill. This means that the power rating designed to meet the gradability will naturally meet the acceleration requirement. So final thing is the vehicle should be able to accelerate easily when it is on grade or when it is on inclination. If the vehicle can accelerate easily when it is kept on grade, then we can say that vehicle is having really high power or drivetrain is designed properly. So in engineering design, the trade-off may be needed between the motor power rating and the system complexity to design an appropriate motor extended power ratio. So power rating design of engine generators, you are finding that the engine generator or EG in series hybrid drivetrain supplies steady power to the prevent PPS from complete discharge. So we have seen the motor design, now we are seeing the powertrain design. So what is the main job of engine generator? That is a primary source. The main job of engine generator is to drive the vehicle, as well as at the same time it will charge the PPS. Charge the PPS means whenever the PPS or battery source is going down or it is getting discharged, primary source should be able to recharge it as soon as possible. So there are mainly two jobs for the engine generator or primary source. One is drive the vehicle, second is it should be able to keep the PPS or battery charged to the extent as long as possible. So in EG design, that is engine generator design, the two driving conditions are: number one, driving for a long time at a constant speed on highway, and off-road hill climbing, driving on a soft road, and driving with a frequent stop-go pattern in cities. So in both the cases, the vehicle should be able to supply very good amount of power or quality power to its transmission. So there are mainly two things what we find in case of any vehicle. One is which one is easy actually, that is driving on the highway, kind of a smooth highway for long time at a constant speed. So this is very easy case. We have seen that PPS graph, we have seen the case B there. Case B was when demanded power is less than the engine generator power. So this is the case, first case what is mentioned here. In this case, whatever is the primary source, that is the engine generator, that can do two things. First, it will drive the vehicle, and second, it will charge the PPS or battery, provided the PPS or battery is not completely charged. Okay, and second thing, which is more difficult, which is the main use of hybrid vehicle, which is off-road hill climbing. Hill climbing might not be done only by the primary energy source. So whenever hill climbing is there, there is a chance that it has to be a driving which will be done by two sources together. So off-road hill climbing, driving on a soft road. Soft road means again higher value of rolling resistance is coming into picture. That means opposition is more. So hill is giving one opposition, soft road, that is rolling resistance is also there, weight of the vehicle is always trying to pull the vehicle down because it is climb. All these negativities are there, and there is added a fourth difficulty which is called as a stop go pattern. Okay, so stop go pattern, soft road, driving with frequent stop go pattern, and it is climbing hill. So all different types of adversity, all different types of resistances is coming into the way. At that time, how well we are able to accelerate, how easily we can go above the hill, all these are going to decide the power rating of engine or generator. That means this is actually talking about how good the PPS and primary source is designed. So in highway driving, the vehicle should not rely on PPS to support the operation at high speed, for example 130 km/h or so. The engine and generator here should produce sufficient power to support the vehicle. But for the second case, as I was explaining, second case means off-road hill climbing. For the frequent stop-go driving pattern in cities, engine generator must produce sufficient power to maintain the PPS energy at a certain level for support the vehicle in hill climbing. That means we should not get the PPS discharged when the vehicle is running through the city with frequent stop-go, because stop-go it is going to actually discharge the PPS source much. Okay, it should not happen that first we have driven through the city, the PPS has discharged, and then we are trying to climb the hill. By the time the hill climbing is coming, the PPS is already discharged and the hybrid electric vehicle is not able to ride the hill. That should not happen. So the energy consumption of the PPS, that is the battery, is closely related to the control strategy. At a constant speed and on a flat road, the power output from the engine or PPS is given as PEG, that is engine generator power, is equal to V, that is the forward velocity, divided by 1000 eta T eta M, these are the gear ratios, mgfr, this is nothing but rolling resistance, plus aerodynamic resistance. So this is the engine power generated in kilowatt when the vehicle is running through a flat road with a constant speed, and the power output from the power source PEG is given by this. You are finding there is no alpha here. Why no alpha here? Because it's a flat road, that's why there is no banking, there is no hill, it is not difficult driving, it is smooth driving. So in this case we are finding that only one component of power energy generation is there, and mgfr and these are actually the opposition that has to be overcome by the engine power. Here eta T and eta M are coefficients of the transmission and traction, and this is the characteristic. So vehicle speed versus load power characteristic is like this. Load power for a 1500 kg passenger car, eta T and eta M not included, but the characteristic of the graph will be remaining same. So you are seeing that load power is around 30, maximum load power is around 38 or 37 kilowatt, and vehicle speed is reaching almost 140 to 160 kilometer per hour. This is what is called as a constant speed and on a flat road, and the power output from the source is there, and it is a very good kind of driving without any very big effort, and there is no hill climbing. So in this case you are finding that the power rating design of the engine generator, so graph indicates that the power demand at constant speed is much less than that for acceleration. It is very easily understandable. That means whenever you are trying to accelerate the vehicle, at that time you need more power from the engine or PPS source. As an example, the power required is about 25 kilowatt, including losses in the transmission and traction motor, eta 0.8 and 0.9, for constant speed around 130 km per hour. So if you are finding average speed, if it is around 130 km per hour, in this constant speed is around 130 km per hour, in that case the vehicle will run smooth without troubling the PPS source or engine generator source much. Even if the vehicle mass is 1500, but the acceleration and all those things will happen in a kind of a constant way. The velocity of the vehicle will be constant. But when the vehicle is driving in a stop-go pattern in cities, it produces engine produced power should be slightly greater than the average load power to maintain the balanced PPS energy storage. Because whenever the vehicle is running through the city, in that case it has to produce some kind of braking, that is called as electrical braking, and that also actually will be added. So electrical braking is producing some regenerative energy, and that regenerative energy will go and it will keep the PPS charged. That is another thing. And whenever the vehicle hybrid vehicle is running through the city in a stop-go fashion, it has to be in a balanced power matter, okay, slightly greater than the average load power to maintain the balanced PPS energy strategy. So average load power in city is given by P average load power. You are finding that previous case the equation was different, in this case the equation is different, it is 1 by T. So power is nothing but, first we are integrating the whole thing, we are finding the energy. So how much is the loss energy and divided by time, this is the loss power. Okay, so this power we have to overcome, because mgfr is nothing but the rolling resistance, half rho acd, this is the aerodynamic resistance, multiplied by V. So this whole integration is wasted energy divided by T, this is wasted power, and this is actually the traction power. So the total power is nothing but from the traction power. If we remove, so from the actual generated power, if we remove the wastage power, we are finding actually the traction power. So right side part is here, delta is the vehicle rotational inertia factor, dv dt is the acceleration of the vehicle. So this is the first term together. So the first term above equation is the average power that is consumed to overcome the tire rolling resistance or aerodynamic drag. That means this is the loss component. And the second term, that is the average power consumed in acceleration and deceleration. So this much power actually is helping the vehicle to go ahead, whether this power is actually pulling the vehicle back. That means this is the loss, and this loss is overcome, and this total power is helping the vehicle to go ahead. Instantaneous and average power in typical drive cycles, you have already seen these drive cycles. So previously it was shown in case of IC engine based vehicle. Now in this case it is shown by electric and hybrid vehicle. So in design of an engine generator system, the power capability should be greater than, or at least not less than, the power that is needed to support a vehicle driving at a constant speed or highway driving and at average power when driving in urban areas. That means the together the primary and secondary source should be able to at least overcome all the losses and get the car going in the forward direction, even if it in the city or it is in any other kind of drive cycle. So in actual design, some typical urban drive cycles must be used to predict the average power of the vehicle as shown in figure. So you are finding the primary FTP 75, it's urban driving because there are too much of stop and go kind of thing. FTP 75, this is a highway driving. Okay, US 06, it is more than city driving, it is more of a highway driving most of the time. But yes, at the starting part and at the end part, you are finding there is stop and go kind of thing. And ECE 15, in ECE 15 you are finding gradually it is becoming a highway kind of driving. So there are 1, 2, 3 stops, but then it is quite a long stretch of so x-axis is time, it's quite a long stretch of high acceleration and good driving experience for ECE 15. So these are different test conditions for hybrid electric vehicle with series kind of coupling or electrical kind of coupling. So operating point of engine generator, this graph also you have seen. So you know that x-axis is engine generator RPM, that is with which speed the generator is rotating, or you can recalibrate the x-axis with the vehicle speed as well. Y-axis is engine generator torque. Engine generator torque is given in torque is generally given in Newton meter, and here you are finding this is the A region. This is the A region, which is the region of economy. Okay, so this region you are finding here output power may be more, but this A region here efficiency is the highest. That means fuel efficiency is highest in this A region. So you will be finding if it is a 0 to 200 kilometer per hour maximum speed, you will be finding around 50 to 120 kilometer per hour. So this is the range for which the vehicle is going to show optimum efficiency or optimum fuel efficiency. So in the engine size design, okay, engine generator size design, the operating point at which engine generator produces the aforementioned power should be designed. So there are two possible designs which is called as A and the B. In case of design A, here the most efficient engine operating point is found. It is point A in the figure. So where is point A in the figure? You have to find. So the center point is the point A in the figure. This is the most efficient engine operating point, where the engine produces required power with maximum efficiency. Maximum efficiency means minimum fuel it will produce very high output power. This high output power may not be the highest output power. Highest output power might be here, but here highest output power is produced at the cost of very high input energy. But here the highest output power is produced with lesser kind of input energy. So this point A or region A, this is having highest fuel efficiency. This is what is said here, point A in figure, where the engine produces required power with maximum efficiency. That means least input, highest output. This design, that means this A design, it leads to somewhat larger engine size, since its maximum power will not be used for most of the time. So if you are at design A, that means if you want the highest efficiency, in this case larger design has to be designed. This design makes power available for special situations, e.g. when the PPS is completely discharged. That means only the primary source has to drive the vehicle. At that time we will be requiring a bigger engine. Later engine power can be also used for a quick PPS charging. That means whenever too much power is produced by the engine, some part will be going to drive the vehicle, some part will be going to charge the PPS, shifting the operating point from A to B. Okay, so you are shifting the operating point from A to B. It causes the bus voltage. Bus voltage means addition of primary source voltage and secondary source voltage. Together they produce the bus voltage, which is given to the electrical motor at the output side. So shifting the operating point from A to point B, that means you are shifting the operating point, that means you are increasing the engine generator RPM. That means you are trying to drive the vehicle with higher speed, more than the optimum speed. So what is optimum speed? This is the range with where the efficiency will be highest, but you are trying to get very high speed from the vehicle. In this case actually you are losing on efficiency. So shifting the operating point from A to B causes the bus voltage to increase, which also increases the vehicle speed. With a properly designed traction motor control, higher bus voltage does not worsen the traction motor operation. On the contrary, higher DC bus voltage enables the motor to produce more power. But design B is having a down point, so design B will be giving you higher output but at the cost of high input. So though here you are getting speed very high, but here you are finding that efficiency will not be very high. So this is what is said here. In the second design approach, operating point is set to point B, which is close to the maximum power. This point B operating point is used for very high to meet the acceleration and gradability requirement. That means if you have to go from Bombay to Pune in the shortest possible time, because you have some very important work, in that case you don't see whether you are maintaining fuel efficiency or not. So for very high speed, for very short kind of time requirement from the vehicle to reach from the source to destination, we are not going to keep our speed within the optimum region of A. In that case we are going to accelerate the vehicle as much as possible, highest gear. We are going to shift the speed from A to B. We are going to get very high speed from the vehicle, but efficiency in that case will be lesser. So in this case the speed, high speed is the requirement, or less time consuming from source to destination is the requirement. But whenever we are in A, in that case if the optimal efficiency is the main required point, we are going to use the point A. So point A and point B both are good depending on what we need. If we need high efficiency, A is the best choice. If we want the shortest time between source to destination, B is the best point. In A, your traveling time will be more, that means you are a slow rider. In B, your fuel economy will get hurt, that means it is going to cost you more financially. So these are the comparison between point A and B. Lastly, we are going to see the design of PPS, that is what is the peaking power source. This we are going to see from this slide. So what is the job of PPS? PPS is generally not coming in the use much in case of hybrid electric vehicle. So the PPS delivers sufficient power to the traction motor at any time. It can give at any time, but it is not called every time. At the same time, the PPS stores sufficient energy to avoid failure of power delivery due to the too deep discharge. So we don't allow the PPS to go below 70%. So PPS is called when too much power is required by the transmission while hill climbing and while in difficult terrain. At that time it helps the primary energy source to ride on a steep hill or on the very difficult terrain and those kind of things. What is the PPS power capacity? So to fully utilize the traction motor power capacity, the total power of the engine and PPS should be greater than or at least equal to the rated maximum power of the electric motor. So PPS plus PEG. PPS plus PEG means total energy produced by the primary and secondary source together multiplied by the efficiency of the drivetrain. So this is PPS plus PEG. This is the total power, maximum power that can be produced by both the sources. As soon as you are multiplying with efficiency, this power is reducing, but then also this total power multiplied by efficiency should be greater than equal to PM max. PM max is actually the maximum power required by the vehicle on a difficult road. So the road may be very difficult, but PM max will be the maximum power required by the transmission system of the vehicle to take the vehicle through very steep situation, to very steep hills and any kind of difficult terrain and all. So total power produced multiplied by the efficiency, which is actually reducing than 100%, should be greater than or equal to PM max. If it is less than equal to PM max, vehicle will go uphill and then it will come down. It will not be able to cross the hill. You just rearrange it. So PPS plus PEG should be greater than equal to PM max by eta m. Then take this PEG in the other side. So what should be the PPS formula? It should be PM max divided by eta m minus PEG. So this is the standard formula for PPS, that is whatever is the maximum required power divided by efficiency of the whole drivetrain minus primary source power generated. So PM max is the maximum load rated power of the motor. That means this is the maximum power that motor can expect, the vehicle motor can expect from both the sources together, that is engine source and PPS source. Eta m is the efficiency of the motor, PEG is the power of the engine generator, and PPS is the power of the peaking power source. So that much was enough actually. Here what we are finding is in some driving conditions where frequent acceleration deceleration happens, that means you are in the city kind of environment where stop go kind of environment is there, it will result a low SOC in the PPS, because too much of stop go kind of things is 0 to T. That means if the T value is, if T is a long stretch, that means when the vehicle is going through a highway. So for a long stretch the primary energy source is driving the vehicle, it is recharging the secondary energy source at the same time. So for this 0 to T, if this is a long stretch, that means energy stored in the PPS will be more. So you are finding this can be you can say this is a kind of a drive cycle if you imagine. So x-axis is time s. So here you are finding here the vehicle started, then this is the zero speed actually, this is stop go kind of thing. Here actually braking occurs. Whenever the braking is occurring, the PPP is getting charged. Then it is kind of a, though there is reduction in the speed, but it is not fully braking. Okay, it is speed is gear is changing and speed is going up and down, but then also it is running quite okay. And then here there may be a very stop for a very small time. Again it is a long stretch for quite a longer time. So this is a considerably good kind of thing as far as PPS charging is concerned by the primary source to the secondary source. So in some driving conditions, frequent acceleration deceleration of the driving pattern would result in damage in the PPS or low PPS, thus losing its delivery power. To properly determine the energy capacity of the PPS, the energy variation in some of the typical drive cycles must be shown. Energy variation in the PPS can be expressed as this. So delta E is equal to 0 to T PPS into dt. It is nothing but the accumulation of energy over a long period of driving. A positive PPS represents charging power. That means this are all above thing. They are actually charging the PPS source by the primary source. And negative PPS represents discharging power. So in this case actually PPS discharging, or if designed properly this can be regenerative braking power. So it depends what kind of situation is there. Energy variation in the PPS is closely associated with the control strategy. Figure shows how the energy changes in the PPS vary with FTP 75 in urban cycle with the maximum SOC control strategy. So E cap, okay, so E cap in this case, so figure also shows the same figure is there. Here you are finding this is 0, above it is accelerating and below it is actually decelerating, or these are braking parts. Wherever you are finding the graph is coinciding with the 0 line, here you are finding that here the vehicle is stopping for very small amount of time. SOC top, SOC bottom, this is the maximum SOC charge 100% generally. SOC bottom for vehicle battery we keep 70%, and what is the total range of change in the PPS, that is delta E max. Okay, so we should know how much is that. Okay, so figure also shows the maximum amount of energy changes in delta E max. That means in the battery what can be the minimum and what can be the maximum energy. Depending on that we can get delta E max, how much is the change in battery energy under the whole drive cycle if the SOC of the PPS is allowed in an operating range between SOC top to SOC bottom. The whole energy capacity of the PPS can be determined by equation above. So this one is this thing. How much is the energy capacity of the battery? It is given by delta E max. That means how much is the change in SOC divided by SOC top minus SOC bottom. Operating range of the SOC of the PPS depends on the operating characteristic of the PPS. For example, for efficiency reasons, chemical batteries would have an optimal operating range from 0.4 to 0.7. So for limited voltage variation reasons, ultra capacitor would only have a limited energy range of 0.8 to 1. So what they're saying is, in certain cases in battery we can find 0.4 to 0.7, that is the SOC of the battery. For ultra capacitor is 0.8 to 1.0. So just you know the graph, but for exam only this slide, whatever I am going to show for exam, this slide is only important. Next two slides are not very important for the exam, but question can be asked only from this slide. So that's all about the primary and secondary energy design and for the series hybrid electric drivetrain. So operating pattern, control strategies, PPS control, thermostat control we had seen in the previous two lectures. Today what we have completed is power rating design. So different formulas are there for power rating or design of traction motor, power rating design of engine and generator. Different conditions have been explained in this case with drive cycles, and design of peaking power source. So for design of peaking power source, only the formula how it comes, that is PPS is equal to overall energy requirement divided by overall drivetrain efficiency minus engine power. So this much is sufficient for peaking power source design. So this finishes the series hybrid electric drivetrain design in case of hybrid and electric vehicle or electric hybrid vehicle. So in module 8 of Ehsani, starting from page number 229, all these details can be found. Next day we are going to start with parallel hybrid electric drivetrain design, and the same parameters or same strategies, control, sizing of major components and operation patterns we are going to see for parallel hybrid electric drivetrain design. So there are 3 to 4 lectures. With that we will finish the whole syllabus. So today this much. We will see tomorrow again. Thank you. Good night.